That's another thing today we're going to learn is a canonical dual map. So I'm going to introduce a dual map, which was the homework problem in the last homework problem, the lecture review of today. So here is no inner product. We did this in a session 1 or 2 in some more general context. B is the basis, V1 through Vn. And we have a vector space spanned by this one. And in your homework, I asked you to think about this new basis, we call it phi1 through Vn, right? And this phi1 through Vn is in where? Linear transformation V2, the scalar f, one-dimensional linear thing. And then the definition of Vk was Vk is going to 1, right? What happened to the other vectors? Zero. Okay? So these were actually the basis of this guy here. And earlier it was actually V to W, and we looked at the basis of V and basis of W, and these were the map we considered earlier, sending Vk to 1 or Vj to 0. Or actually to vectors, you have to assign the vector. So it's a lot simpler case, and then this becomes a basis, and that was a homework problem. All right? And so map between those things, so anything, because of that, anything that is inside this linear transformation is going to be written in terms of linear combination of a phi k in the k1 through n. All right? This was hard back then because phi k is not column vectors, right? Phi k is not this vector that we're talking about. Phi k is a linear transformation. And how do we establish things like that between some of the function? You have to plug in something to establish this equality between function, right? But what this one says, if this is a basis, anything you pull it out must be linear combination of Vk. How do we verify this one here? By plugging in V1, V2, V3, all the way to Vn. Right-hand side V1, V2, V3. If they're equal, and they're equal. Okay? So that was that. And the dual map equals a dual map is the following. Psi sending this V is a vector, and this LVF is a linear transformation. What was the dimension of this guy? Anybody remember the dimension of this one? Dimension of F times dimension of V. Okay? That was actually the matrix space. N times n. But what is the dimension of F? 1. Right? Because it's a scalar. So that's why it's a dimension F. Dimension V. Which is n, right? So if you're looking at the n-dimensional space to n-dimensional space, there's always an isomorphism. What a dull statement, right? N-dimensional vector space to n-dimensional, there's always an isomorphism. You choose a basis and send the basis to basis, and that's an isomorphism. So without inner product, map between vector space is not that interesting. And here, the map, I define it in there, I'm sending Vk to Vk. In general, I'm sending all the AK Vk, which is a vector, right? Sending it to AK phi k. That's a linear transformation. And I claim that this is a linear transformation. And it has the null space 0. Same dimension, null space 0, it must be isomorphism. Remember that part? Rank theorem. Yeah. So this is an isomorphism. Let's see why the null space is 0. Why is the null space is 0? All right, so here, suppose this thing, okay, we're looking for vector under this connection, it becomes 0, right? So vector sent to where? Where does that go? So this is 0. So what is the image of AKVK, sum of AKVK under this map? By definition? AKVK goes to AKVK, right? So here's the AKVK is a 0. That's what this null space is about. A vector that ascended into linear transformation like that linear transformation is a 0 linear transformation. All right? And we want to show what? AKs are all 0, right? So how do you establish two functions are equal to something? You have to plug in vector in there. To establish that two functions are equal, you have to evaluate that functions, right? So what do you think? Where should I evaluate this function? It's AK, VK. Does it look like a name of a function? And I'm applying something in here, right? And this part is going to be 0, always, no matter what you plug in. All we want is to identify what is these AKs, and what is it we want to plug in here. What do you know about VK? You're going to plug in here so that you use something you know about VK, right? What do we know about VK? This is what we know about VK, right? So what do you want to plug in? VKs, right? Since I already used this case here, I'm going to call VJ. Is that okay? I'm going to call it VJ. Plug in VJ and see what happens. So VJs apply to everywhere. You can imagine this is sum of two things. Applying an element of function, it distributes over, right? Doesn't matter if it's linear or not. It has nothing to do with the linearity of a phi. So k equals 1, n, ak, and that is applied in here. Is that okay? Make sense? What do we know about vk and vj? Most of the time, they're 0. This particular linear transformation only survives when this is vk. Everything else in the base element is 0. So these are all zeros, except when k hits j, right? So there's aj, vj, vj is the only thing that survives. But what is vj, vj? By definition, that's 1. That picks up 1. So what do you say? aj is 0. Okay, we did this one, believe it or not, back then, and to show that it's isomorphism and injective map between this thing. So like that. All right. So that's why this one is. There's no inner product. Let me tell you that when you're establishing a map from here to there, it's heavily depending on your choice of basis. If someone else to come up with a different basis, this map from vector space to the functions on vector space. Does that make sense? Vector space to connection to function in vector space is going to be changing if somebody use a different basis in there. All right? So what is this? This is our space, like Euclidean space, n-dimensional, 4-dimensional space, like space-time. And what is this one in here? Functions building on top of that. And this happens to be the very, very important theme in mathematics. If you want to distinguish some odd-looking two things, and you want to, show that this is not isomorphic to something, and what is the idea? Don't look at this, guys. It's too complicated. Something simpler, something more algebraic, something not too geometrically complicated, is that they look at the functions that is defined on that, which is this one here, right? This is some geometric space. This is a functions that are defined on that. So you see this a lot in higher mathematics. If you want to study this one, don't just study this one. Look at the functions. Then we have algebra attached to that, purely geometric problems, right? That is amazing accomplishments from Raja Penrose and other mathematicians to approaching in a general relativity and space-time algebra into this way. Of course, physicists never do this. It's mathematicians' idea to actually approach an algebraically like this. So it's an important business. Here's a v and a function that are attached to it. And this is bad because this function is depending on your choice. If somebody chooses a different basis, it's going to be a completely different connection between these two important worlds. So that's where the inner product kick in. Inner product allows you to make these two connections without choosing a basis. Okay? That is canonical dual map. All right? I'm saying that, this depending on that, but it's not obvious. I choose a different basis. Maybe it's the same map. You actually have to try it. It's a different map. All right, so no inner product. There's this dual map, ugly dual map. It's complicated. Here's the pretty dual map with inner product. All right, so what is the idea of psi going to from V to where? Functions on that V, right? Linear transformation. So what is the map? So here's given by, with inner product, we're going to use inner product, given by psi of vector V. W, they use W, so I'm going to use W. So this is a vector space V. What is it? They call it phi W. All you have to focus on is that I don't use bases. That's all you have to focus on. So I just named that linear transformation where, so what is it? Now I'm evaluating. If this is a linear transformation in here, if I plug in a V, how do you evaluate this one? That's all you have to define it, correct? Okay. A vector W is mapped to linear transformation. VW, just a notation. So I have to explain what that VW is. If I plug in a vector, if it is coming from here, right? Right there. If I plug in V, how do you evaluate it? The answer is do the inner product with a W. So if you see W down there, V up there, how do you evaluate this linear transformation? Inner product in this order. And W going to the second slot is important because it's not quite linear in the second slot because of the conjugacy. And you flip it over. It's only linear in the first slot because of the scalar multiple. If I do the scalar multiple, when it pulls out, it doesn't pull out K, it pulls out K bar, right? So it has to be linear on V. V must go to the first slot, so scalar multiple K pulls out. Make sense? All right. So then, first of all, you have to understand why is this linear? Why is this linear? That's one thing you have to understand, right? I define it this way, then why is it linear? So that it actually is in there. Fair enough? That's one question. I just gave you the definition and you have to show why is this phi W is in here. Why is it linear? I'll leave that as an exercise. Very, very simple. Just a linear product. So that is, what is the name of this map? It's called dual map. This duality appears in all sorts of higher mathematics, is particularly talking about this one. It arises in many fancy contexts. Whenever you discover some nice pairing, something nice going on, most of the time is a dual map. You try to put it into this context. The reason these two things are so behaving nicely because if there is a dual map behind the scene, and this is the map, and it is good, we call it a canonical. If there's an inner product structure, there is nice structure in that. So they introduce this notation. Notation for this one is V star. Okay? V is a vector space. What is a V star? Functions on that vector space. And this is not just a linear function whose image is actually scalar, right? That's a special. So we call this a linear functional. Not from V to W, but V2 is a scalar. That's a very special linear transformation with a huge kernel. Do you see that? This one sends a large vector space all the way down to one scalar, right? What is the dimension of the kernel? What is the dimension of the null space? N minus 1, rank theorem, right? Because your range rank is 1. All right, so it's important. It's a canonical thing in there. All right, here's an example. All right, first of all, I give you this definition, and also you have to think about why is this psi linear? That's something you have to think about, right? And in this context, you also have to show the null space of psi is 0, which I showed earlier in the choice of bases and all that, right? If the null space is 0, then you see this is isomorphic. If V is a finite dimensional. Rank theorem, right? Dimension n, we already showed the dimension, right? Dimension has nothing to do with this map. Dimension of this one is n. Dimension of that one is n. Null space is 0. Then it must be isomorphism. Correct? Yeah, that's all that thing is important. So this is canonical dual map from V to V star. That's usually how people state in inner product space nicely. And here's an example of evaluating this. So here's an example. Polynomial of degree 3 with a real coefficient. That is our V. And what is the dual map is the following. So if I have a dual map as a polynomial, the polynomial written like P here. Is that right? Vector in here is a polynomial. Make sense? So what is this one by definition? Phi of subscript P, right? That's a linear transformation, correct? Where phi of P, not phi of P, phi subscript P, what should I plug in here? Some polynomial Q, because this is a linear transformation on the polynomial world, right? So where is it? Linear transformation from a polynomial to the scalar R. So that's what this phi is. So if I plug in polynomial, it should spit out a number, right? Right? Okay, so what was the definition again? Phi PQ. Remember this one? Was the inner product, right? Where does the P go? Front and back. Back here. Because it has to be linear on Q, the scalar linear part, we have to put in there. So that's the definition of this linear functional. Phi PQ. Alright, what was the usual inner product that we defined in here? Polynomial? Integral from where to where is not given, right? So it has to be given if it's in our product space. Let's say that was A to B whatever. Then what? Q times P conjugate usually, but here's a real world, so conjugate is not necessary. That was a Hermitian inner product, but here's not. So whatever the polynomial you have over the real number, you multiply, integrate over A to B, and that's the map in here. There's no choice of bases. It's a nice one in here. Let's see if I've written down anything. All right, so for example, psi of, let's say that was 1 and negative 1. That's a nice one like that. Make sense? Let's try x plus 1. What is it? Phi subscript x plus 1, right? That is a linear transformation. And what kind of linear transformation is this? We only know by plugging in some polynomial q in there, right? This linear transformation sending it to number. What is that? Inner product from negative 1 to 1 of q first, right? Here it really doesn't matter because if it's real, but it's a conjugate complex, it makes sense. It matters. X plus 1 dx. All right, that's the map psi. If you have a vector, send it to a linear transformation. How are we going to actually evaluate the linear transformation? We use inner product. Inner product gives you a number, a scalar, right? So that's the thing.